Good evening, everyone. I welcome you all on the behalf of StudyIQ IAS English. My name is Pritesh Maturkar. I extend my warmest regards to those who are watching me for the first time today and also to those who are continuing these sessions with me. So, today being the 21st lecture of this series, and today being the last lecture in the sense that from tomorrow onwards, we will be migrating into the thorough analysis of the maps. So, it gives me utmost privilege, it gives me immense joy that you and me are both together entangled in this beautiful journey, and that you are all in consonance with me, and that I, as your able philosopher, mentor, and guide, is able to take you all on a world tour wherein we are able to understand the earth's physiography, wherein we are able to understand the aesthetic beauty of earth using the most potent tool of the discipline of geography called as maps. So guys, up till now we have focused on the Earth's atmosphere. We did discuss the Earth's lithosphere, the Earth's land surface. Today we will be venturing out into discussion of the Earth's hydrosphere per se. From tomorrow onwards, we will start our detailed analysis, our detailed foray into the maps per se. So I welcome you all. I extend my warmest regards to everyone, to those who were continuously watching with me. So a typical workflow of these sessions is like this, that in first 5 to 10 minutes, I tend to revise whatever we did in the previous lecture, and then I introduce you to new topics, and thereafter we try to use maps to understand its practical utility. And whatever content I was showcasing you on the board, I've always showcased the content which is having direct utilitarian value in prelims as well as mains. So using this curriculum, I tend to cover roughly 50 to 60% of your GS geography discourse, and using this you will be pretty able to understand the advanced level concepts too. So this curriculum or this series can be used as a bedrock for your GS preparation. And most importantly, in this series, in this curriculum, we are trying to interlink current affairs too. So wherever possible, I am trying to cringe in the current affairs too for you all. So welcome all, most official welcome to everyone. So let's begin our journey. Let's continue our journey forward. As promised, guys, each day of this journey will begin with a beautiful picture, with a beautiful location, which I covered in the previous class. Morning, Sumit. So I'm saying morning because it's the first time you and me are meeting. So good morning, everyone. I hope that you have risen up properly, you have worked hard properly, and that your morning is going on fine. Okay, okay, okay. So you are a newcomer, Sumit. Don't worry, you will be pretty comfortable with me. Just imagine that this is your first class today because up till now I have not started maps. So most official welcome to you because tomorrow onwards I will be venturing into the first map of the world, that is New Zealand. So a welcome initiative to you. Let's begin our session. So the location which you are seeing behind me, the picture which you are seeing behind me, if you can see this particular this particular fault, this is called as, guys, San Andreas fault. You remember that yesterday we did plate tectonics, and in plate tectonics we discussed the third type of interaction, that is the transform boundary interaction, wherein the two lithospheric plates, they just slip past one another. Okay, they don't basically move into, neither they are moving apart from each other, so neither they are converging nor they are diverging, they are just slipping past one another. So such kind of interaction is called transform interaction. And in such interaction, will you have volcanism? No. Can you have seismicity? Yes, you can have earthquake. So this is what you find. So on this side, you have the which plate? You have Juan de Fuca plate, and on this side you have the North American plate. So the Juan de Fuca plate is just doing what? Is just slipping past the North American plate, result into creation of San Andreas fault. So entire west coast of USA, you have Los Angeles, you have San Francisco, you have San Diego. All of this experiences immense amounts of earthquakes because of this fault. Okay, and in the future it is estimated that this entire fault will become active, and the complete west coast of USA, like starting from Sacramento, from Los Angeles, San Francisco till San Diego, will be drifted apart. So you will have this activation of this fault will grow into, and this complete part will be taken out of the North America's plate. So this is called as San Andreas fault, and most importantly, this is a transform boundary interaction wherein the Juan de Fuca plate is just slipping past the North American plate. And guys, this is the beauty of this discipline, that whatever I'm teaching you, you are all able to see it with your eyes, you are all able to feel it with your eyes. So nothing gives me more joy than actually making you realize that how beautiful our earth is, how beautiful this discipline is, and how beautifully everything connected is. Okay, so let's begin our today's session. So quickly, just let me do a recap of whatever we did in the previous class. So in the previous class, I did introduce you to the concept of plate tectonics. So in the concept of plate tectonics, we did opine that the lithospheric plates, they are drifting and moving over what? They are drifting and moving over the semi-molten asthenosphere. The lithospheric plates are grouped into two major groups. You have the major plates and you have the minor plates. As these lithospheric plates basically collide or they diverge from each other, you have three different types of interactions. So the first type of interaction that we did yesterday was the divergent interaction, wherein the two lithospheric plates basically diverge from one another. And how does this divergent boundary form? How does this divergent boundary originate? It originates via what? Via mantle plume beneath the surface of earth. So if this is the earth's surface like this, below this you will have a mantle plume like this. Because of this, the surface of the earth will experience what? It will experience a thing called as domal uplifting. So here now you will have localized volcanic eruptions. So this is called as what? This is called as domal uplifting. So after this, what will happen? The piece of continent, it will start to stretch, it will start to thin before it rifts like this. So it is starting to stretch, it is starting to thin before it is rifting. So now you will have formation of a nascent sea over here. This nascent sea or nascent ocean, it is very much evident in where? It is very much evident between Africa and the Saudi Arabian plate. So between the African plate and the Saudi Arabian plate, you have the Red Sea. So this is this stage wherein you have stretching, you have rifting, and then finally you will have the breaking up of the continent. So this is the third stage, and then lastly you will have what? The last stage will be the formation of a proper mid-oceanic ridge at the ocean floor. What is mid-oceanic ridge, guys? So the mid-oceanic ridge is like a actual rift valley at the bottom of the ocean floor like this. Okay, so this is our mid-oceanic ridge. Here you have continuous volcanic eruptions. So this is our mid-oceanic ridge, and the mid-oceanic ridge is basically what? It is the location of ocean floor creation. It is the location of ocean floor creation. Okay, it is the location of ocean floor creation. So every divergent boundary will begin with a mantle plume within a volcanic plume beneath the continental plate. Then you will have domal upliftment. The continent will stretch thin, slip apart, resulting into formation of nascent sea. And then lastly, we'll have the formation of the mid-oceanic ridge. So I did explain you with regards to the Atlantic Ocean. So on one side you have the American plate, you have the North American plate and South American plate. Here you have the Eurasian plate and the African plate, and in the middle you have the Atlantic Moor. So Moor is basically the location of ocean floor creation, and as the ocean floor is created, it is destroyed where? It is destroyed at the trench margins. I will explain you what is trench margins. So on earth basically we don't have older oceanic crust below before the era of dinosaurs, whereas the continental crust once formed is never destroyed. Why? Because continental crust is lighter, it is buoyant, so it resists subduction, whereas the oceanic crust is heavy, it is denser, it gets pulled into the mantle, it subducts and it gets melt. So as the oceanic crust gets melt, it gets recycled. The cycling process is called as Wilson cycle. Hence, on Earth, we do not have older oceanic crust older than the Mesozoic times, older than the era of dinosaurs. Whereas continental crust you will find on Earth, which is very, very old. Recently, last year only in November in Australia, you had the continental crust being discovered of roughly 4.2 billion years old. Okay, so we do have continental crust which is so goddamn old. Even in India, we have the world's oldest mountain range. All of you must be knowing the name of the mountain range we discussed. It is the Eastern Ghats. Okay, so this is the divergent boundary. The second kind of interaction we did was the convergent interaction. What is convergent interaction? So convergent interaction is basically the two lithospheric plates colliding with one another. So just imagine these are the two plates, they are now approaching one another. And as I told you guys, normally you will have what kind of arrangement? You will have arrangement continental plus oceanic. Rarely you will find purely continental plate or purely oceanic plate. You will have oceanic margins in front of the continental plates. But mind you, oceanic plates or oceanic margins are not the extensions of the continents. Oceans are more fundamental in nature as compared to the continents. So, in convergent interactions, you will have three types of interactions. The first in the sequence will be the OO kind of interaction between the two oceanic plates. The second will be the OC interaction when one oceanic slab is completely melted and now the other continental slab is now facing the oceanic slab, and the third in this sequence will be the CC interaction when both the oceanic plates have been completely subducted and the two continental plates are now facing each other. If we want to show this diagrammatically, so OO interaction will look something like this. So imagine this is our continental plates. Over here we have the oceanic margin like this. So this is our oceanic margin. Now here also you are having one continental margin like this. Okay, but this oceanic margin is now subducting underneath this oceanic margin like this. So this is our OO kind of interaction where one oceanic plate is subducted into the mantle like this. So OO kind of interaction. So this is our C, this is our C, this is our O, this is our O. So one of the oceanic slab is getting pulled beneath the mantle underneath the other ocean slab. In OC, what will happen now? Now the oceanic plate will get subducted underneath the continental plate. So now this is our continental plate like this. So this is the continental plate now. Now the oceanic slab is getting pulled underneath this continental plate. This is our O boundary, this is our C boundary. So this will now be the zone of interaction. Whereas in CC, the two continental plates will come face to face. The two continental plates will now come face to face and you will have immense compressive forces. So you have OO interaction, you have OC interaction, and finally you have CC interaction. If I'm trying to paint the picture of OC kind of interaction, so let's move to the details of OO and OC interaction. So now just imagine you have one oceanic slab like this. So this is your one oceanic slab like this. Okay, let's assume that we are drawing it in 3D. Okay, so this is our one oceanic slab like this, and you have another oceanic slab which is subducting underneath this particular slab. Okay, so you have another oceanic slab which is basically subducting beneath this. Okay, so this is the other oceanic slab which is subducting behind this. Okay, so as this oceanic slab is subducting underneath this, over here you will have what? You will have clustering of sediments of the subducting ocean slab at the edge of the other ocean slab. So this is one ocean slab, this is another ocean slab. So this is one ocean slab, this is another ocean slab. As this ocean slab is being pulled into the mantle like this, so at this edge, at this age, look at my hand movements like this. So at this age, you will have plastering of sediments of the subducting ocean slab. This plastering of the sediments at the zone of subduction, this is referred to as accretionary prism. This is referred to as what? Accretionary prism. Okay. And the zone of interaction where the ocean slab is being pulled into the mantle, this zone or the boundary of subduction, this is called as trench location, where you have the zone of subduction. So if I am saying that what are the features of O kind of interaction, so you have one active subduction zone which is called as trench location. It can go up to 700 kilometers deep, so zone of subduction. Okay. You can also have accretionary prism. So this accretionary prism is basically the sediments of the subducting ocean slab which get plastered over here. And now as this ocean slab is subducting, its sediments can melt, they can rise up on this slab, and they can form what? They can form long linear chain of volcanic islands over here. This will be called as volcanic archipelagos. This will be called as volcanic archipelagos or volcanic islands. So along the O boundary, you will have volcanic archipelagos, you will have the accretionary prism, and you will have the trench location. Anything to the back of volcanic archipelago, this is called as back arc, and anything to the east of that or after the volcanic archipelago, this is called as forearc. This is called as forearc. So if I'm trying to paint the picture of OO boundary or OO interaction, so first of all you will have what? First of all you will have the volcanic archipelagos lined like this. Okay, then you will have what? You will have the zone of interaction, you will have the trench location, and in that trench location on this edge you will also have accretionary prism, and this is how you will have the subduction. So anything back of this volcanic archipelago, this is called as back arc. This is called as back arc, and anything in the front of volcanic archipelagos, this is called as forearc. Okay, so the back arc basin will have what? The back arc basin will have marginal seas. The back arc basin will have marginal seas. Okay, I know this is little bit daunting, guys, but all of this information will come in handy from tomorrow onward. So finally you will be able to realize the gravity of me venturing into the plate tectonics like this. And the forearc basin will have what? The forearc basin will have the accretionary prism, plus it will also have the trench location. So this is the back arc and the forearc, and these are the features associated with the OO boundary. Now after O boundary, we did do the OC boundary. So at the OC boundary, what is happening? So imagine this is our continental plate like this. Okay, so this is our continental plate like this. Okay, and beneath this now you are having subduction of oceanic slab. Now the oceanic slab is subducting underneath the continental plate like this. So this is our continental plate and this is our oceanic plate. So this is how you are having subduction like this. Now just imagine at this zone of interaction where this subduction is occurring, you will have what? So this is the second in sequence. First the boundary was of OO type. Now one complete oceanic plate has been subducted, and now this oceanic slab is facing the continental slab, and now this oceanic slab has begun to subduct. So over here now you will have a new mixture of what? At this zone of interaction you will have three types of features. Number first, you will have the older accretionary prism when the boundary was of OO type. You will have the older volcanic archipelagos, and then you will also have what? You will also have the pieces of the continental plate too. You will also have the pieces of the continental plate being chopped, being deformed, and being plastered along the zone of interaction. So you will also have continental pieces being chirped. You will also have the continental pieces being chirped. And this 1 plus 2 plus 3, 1 plus 2 plus 3, this new chaotic mixture, this is called as what? This is called as melange. This is called as melange. So if I'm considering the OC zone, then you will have which mixture? You will have melange. Remember, when you will have OO boundary, you will have accretionary prism. When you will have OC boundary, the new mixture will be called as melange. Melange will have what? It will have the older accretionary prism, it will have the older volcanic archipelago, and it will also have the continental pieces. The continental pieces of the slab which against which the oceanic plate is subducting, and this melange will uplift. This melange will uplift as long linear chain of mountains called as the Andean type of mountains. So we have done the Andes of South America. So that is what is happening. So what are Andes of South America? They are nothing but the uplifted melange of the OC boundary. So please get this very straight. In O boundary, you will have accretionary prism. In OC boundary, you will have melange. And the third type of interaction that you have is CC interaction, wherein two continental plates are now directly facing each other, and you will have what? You will have immense compressive forces. So because of this, it will result into formation of folds like this. So when two continental plates are basically colliding, you will have immense compressive forces. You will have immense comprehensive forces. You will have immense comprehensive forces, and these forces will result into the folding and buckling of the continents. So you can have different types of folds, and this will result into formation of the fold mountains of the earth. So we did discuss the three types of mountain building phases: the Caledonian phase, the Hercynian phase, and the tertiary alpine mountain building phase. So if I'm painting a crisscross picture in front of you with regards to OO boundary, OC boundary, and CC boundary, so OO boundary will have what? It will have volcanism, but that volcanism will not be as violent. Why? Because the magma which comes out is basalt, and the basaltic magma is basically very fluidic. It flows like a river. You remember we did discuss the Hawaiian hotspot eruption. So it flows like a river. So if I'm considering O boundary, volcanism is high, but the seismicity is less. If I'm considering OC boundary, volcanism is little bit subdued, but seismicity is now increasing. But if I consider CC boundary, then you will have no volcanism, but very high seismicity. And the example of this is the Indian plate colliding with the Eurasian plate. So as Indian plate is colliding from the south with the Eurasian plate, you have upliftment of Himalayas. So Himalayas are the world's youngest mountains. Himalayas are the world's tallest mountains. Why Himalayas are uplifting? Because of the collision between the Indian plate and the Eurasian plate. So you will have very high seismicity. And the last type of plate boundary that we discussed was the transform boundary, wherein because of the slippage, wherein just the interaction of two plates, these two plates then neither collide into, neither they are diverging. They are just slipping past one another. So where my nails are basically chirping against each other, this will be called as the transform boundary interaction. And that is what I showcased you in the opening of session, the location of the San Andreas fault, wherein you have the transform boundary interaction of Juan de Fuca plate with the North American plate. So guys, here I sum up the discussion of the lithosphere of Earth. Here I sum up the discussion with regards to the land surface of Earth, which I felt was important for covering maps. So this is roughly 30 to 40% of your geomorphology, whatever I've given you an overview. Rest of the advanced concept will follow in your GS discourse eventually, but this was enough for you to understand locations of the different trenches, the locations of the different volcanic archipelagos, which we will start from tomorrow. So 20 lecture series to build up the base, then we will start venturing into detailed map analysis. So now I'm opening up the last sphere for all of you. I will be discussing in very short the hydrosphere for you all. Okay, the hydrosphere for you all. those who are watching me, I hope that you are in consonance with me. Those who watch me at a later time as per your convenience, I also have faith that you are moving shoulder to shoulder with me. And guys, see, don't worry. What I'm trying to say is that you have to have some faith in the sense that first we have to build up the base, and then as we have built up the base, we will start analyzing the maps. Because if I'm directly opening up the maps for you, it will not solve the purpose, and tomorrow it will be evident when I will start a discussion of New Zealand, because we will be discussing plate tectonics of New Zealand, we'll be discussing the volcanic peaks, we'll be discussing the rivers, the valleys. So all of this knowledge will surely come in handy for each and every one of you. So the last kind of foray into our database discussions in this series is with regards to the hydrosphere. So if I'm considering the earth, 75% of the earth's land surface is covered by water. So earth is basically a blue planet. 25% of the earth is land, rest 75% of the surface is water. So just let us try to understand the temperature and salinity of the oceans. These two are very, very important features with regards to understanding the hydrosphere. So let us begin with the understanding of the temperature of the oceans. Okay, the temperature profile or the temperature of the oceans. So this has got a very close relation with the atmosphere too, because whatever trends we see in the distribution of land temperatures, the same kind of distribution we see with the oceans too. So on an average, the temperatures of the oceans, I'm again reiterating, on an average the temperature of the oceans is around 3 to 4 degrees Celsius. This is the average temperature of the oceans globally. Please get this very, very straight, don't get confused. Okay. Sumit, Vishal, you are asking, sir, earthquake hit in Turkey is due to the friction between two plates or just the less of rigidity of olivine? No, Vishal, olivine's rigidity has nothing to do with earthquake. The earthquake which happened in Turkey was because of the ancient fault line which got activated. So Turkey is basically a transform boundary zone. Okay, from the south you have the African plate which is squashing, and from the north you have the Eurasian plate. Between these two you have the Anatolian microplate of Turkey. So Anatolian microplate of Turkey is basically trying to escape. So as it is trying to escape, if you are asking me this, so let's understand that also. Let us try to answer your doubt also. So understand this. Let me use the diagram. Let me use the atlas so that you have a clear bird's eye view of what I'm trying to say. Okay. So this is Turkey. Okay. So what is happening in Turkey over here is that you have a plate called, a very small plate called as Anatolian plate. Anatolian microplate. So this is called as Anatolian microplate on which the Turkey is built. So from the south you have the African plate which is squashing, and from the north you have the Eurasian plate which is squashing. So basically the Anatolian plate is trying to escape this part. So just imagine you have this plate and you have this plate, both of these plates are squashing, and this small plate, very small little fella, is trying to escape this pressure. So your mains is approaching, your prelims is approaching, your mind is now popping out. What should we do? UPSC should fail. Okay, there must be an earthquake, something should happen, exam should not be conducted. The same thing is happening over here. So because of this you are having two fault lines. Fault lines means what? Wherein you have this tension being released, wherein you have this intense pressure being built up. Because of this, the ridges, the faults are being created. So you have one fault which runs from the northeastern part of Turkey towards southwest over here, and this is the region where the earthquake actually happened. So if I'm zooming in, okay, so if I'm zooming in this part, let me just clear this up. Okay, so this was the region. This is an active fault line in Turkey, and this is the region. This is a city called as Gaziantep. This is called as Gaziantep, which is resting on an active fault line. So whatever stresses will build up because of this washing, the stress was built up and the stress basically got released. So just imagine this, you have this kind of tension being built up at this location, and immediately as the stress is beyond the carrying capacity of the surface, it is being released like this. So that is what happened. So the fault line became active across Gaziantep, and you have one of the most devastating earthquakes in the history of Turkey. And mind you, this region also experienced aftershocks of same intensity. It's very unnatural, okay, that you are having the major earthquake of more than 7 Richter scale magnitude, and you are also having aftershocks of around 6.8, 7.2 Richter scale. So indicating that this region is very, very tectonically active. Okay. Vishal, most of the earthquakes are not in this region. Most of the earthquakes are in the Pacific Ocean. It is called as Pacific Ring of Fire. That is for a later date of discussion, because then I will have to explain you the entire geomorphology. But just know that this is why, because the Turkey is sitting on two active fault lines. The Anatolian plate is trying to escape this region. So this can be asked in your prelims if you are attempting, whereas the world's highest earthquakes, they come in the Pacific Ring of Fire region. It is called as PROF, or it is called as a circum-Pacific belt of volcanism and earthquakes. Okay, so let's start with the discussion of the hydrosphere. Let us quickly do the temperature profile of the oceans. So on an average, the temperature of the oceans is between 3 degrees Celsius to 4 degrees Celsius globally. Okay, so this is the average temperature of the oceans. But if I'm trying to paint the vertical temperature profile of the ocean, where do we have the surface temperature, the middle temperatures and the lower temperatures? So the surface profile of the temperature of the oceans is somewhat different. Okay, how it is different? So if I'm considering the surface temperature of the oceans, so where do you think you will have the warmest of waters? Will you have the warmest of waters on the equatorial areas or in the tropical areas? The answer is, you remember, which are the world's hottest areas? Are the world's hottest areas equatorial areas? No. The world's hottest areas are tropical areas. Why? Because in tropical areas you have high pressure conditions. Because of high pressure conditions, you directly have insolation of the sun reaching the surface. Hence, you find majority of the deserts at the subtropical locations. Similarly, if we consider the surface temperatures of the oceans, so the highest surface temperature of the oceans will not be at the equator. The highest surface temperature will be at the tropical locations, will be at the tropics. Whereas at the equator, the temperatures will be somewhat subdued. Why they will be subdued? Because of intense rainfall. On equator, it keeps on raining throughout the year, and as it rains throughout the year, it basically cools down the surface temperature at the equator. Yes, Vishal, you are right. So the surface temperature, if you see, they will be highest at the tropics and they will be lowest at the equator. And as we move ahead, like in general, the temperature of the oceans will decrease from equator towards the poles. So same thing with the land surface too. In general, the temperature as from the equator towards the pole will decrease. But there is a catch in this. Okay, we need to understand the catch, like how this catch is and what is this catch. Let us try to paint using diagram. Okay, so if I'm considering the temperature profile of the oceans, so it is somewhat like this. Okay, please bear with me on the board for a moment. This is very, very important. So let us assume that this to be the temperature and this to be the depth of the oceans. Okay, so I told you, on an average, the temperature of the oceans is between 3 to 4 degrees Celsius. So let us assume that this is the average temperature of the oceans. This line represents 3 to 4 degree Celsius. Okay, so this is 3 to 4 degree Celsius. Now, where am I saying you have the world's highest oceanic temperatures? The world's highest oceanic temperatures are at the tropics. So There is a layer between 5,000 meters to 10,000, between 5,000 meters to 100,000 meters. This layer is called as there is a layer between 5,000 meters to 11,000 meters. Okay, this layer is called as what? This layer is called as this layer is called as thermocline. This layer is called as thermocline. This layer basically acts as a lid. This layer will basically act as a lid. It will act as a lid between the layers above and the layers below. So thermocline will maintain the average temperatures of the oceans between 3 to 4 degree Celsius. So if I'm considering the temperature profile of the oceans, it is somewhat like this. So first of all, I'm considering the tropical areas. In the tropical areas, the temperature of the oceans is between 23 degrees Celsius to around 27 degrees Celsius. So this is the temperature profile of the oceans at the tropics. As we go near the thermocline, the temperature profile becomes like this. Now, mind you, at the equator, is the temperature highest? No. So at the equator, the temperature profile is somewhat like this. So this is what? This is equatorial modification. Why we are calling this equatorial modification? Because at the equator, you will have intense amount of rainfall which will reduce the temperature. So this will be the equatorial modification. After this, again, this line will move like this. If I'm considering temperate areas, so in temperate areas, the land will be again somewhat like this. Okay, let me use it more beautifully. So let me just paint it again. So along temperate areas, the temperature profile will be somewhat like this. So this is the tropical, this is equatorial, and this is temperate. So as we move from equator towards the poles, there is a slight change in temperature profile. The warmest of surface waters are at the tropical areas. Equatorial areas will have slightly less hot waters, whereas the temperate areas will have even more hot waters. Now, if we go at the poles, this is very, very important. If we go at the poles, what is happening? At the poles, the temperature profile is reversed. At the poles, the surface temperature of the waters is 0 degrees Celsius. So the surface temperature is 0 degrees Celsius, but with depth, the temperature rather increases. How is this possible? With depth, the temperature rather increases. Why? The answer is linked to the okay. So before I move ahead, I will like to paint a little bit naughty incident of each and every one of your childhood. So you remember that in the childhood, you used to play with the refrigerator. So if you put up a water bottle filled with water in the refrigerator, and in the morning, if you open up the refrigerator, so the water bottle size would have been swollen, the water bottle would have been swollen, and seeing that, your parents would have hit you, you would have gotten scolding from your parents, and your head would also be swollen. Why is this happening? Because once you start cooling the water, so as the water cools below 4 degrees Celsius, it expands instead of contracting. You remember this? We did this when we were small kids, when we were in the 8th and 9th standards. You must have done this in the school. You must have learned with regards to this. So this is which kind of behavior of water? So this is the amorphous expansion of water, that if water is cooled below 4 degrees Celsius, it expands instead of contracting. So at the poles, same thing is happening. At the surface, the water temperature is 0 degree, but as you go with depth, the water temperature increases. Why? Because water, instead of cooling, it is expanding. It is what? It is expanding, because water expands if cooled below 4 degree Celsius. So at the poles, the temperature profile is slightly reversed. So please remember this temperature profile of the oceans, that the warmest waters you find at the tropics. Equatorial regions will not have the highest temperatures of the waters. they will have little bit slightly less. Why? Because of incessant rainfall. Temperate areas again will have this general trend, and at the poles the temperature profile is reversed. Please keep this in mind very properly. So this is with regards to the temperature of the oceans, nothing more to discuss. And if you have rivers draining into the oceans, if you have big glaciers draining fresh water into the oceans, so those areas where you have large influx of fresh water, you will have large influx of glacial water, there also the temperatures will get reduced. So if I consider the Black Sea region of the world, okay, wherein four major rivers of Europe come and drain. So in general, the Black Sea will have lesser temperature as compared to the other areas. Why? Because of influx of fresh water, because of influx of addition of waters by the rivers. So similarly, if I take you all to the Arctic Sea, to the North Sea, to the Baltic Sea, there also, because of the melting of the glaciers, because of the melting of the polar ice caps, the temperatures of the water will decrease even further because of fresh addition. So this is how you have variations in temperature globally. Slowly, as we do the locations, we will understand this even further. So this is a very simple understanding of the temperature profile of the oceans. Now let us also discuss a little bit about the salinity of the oceans. Guys, like I'm blistering to this, don't worry, I'm only discussing those things which are important from mapping perspective, nothing more than that. Okay, so salinity wise, okay, you need to understand that you have four major salts in the oceans. Out of that, the most major salt or the most important salt, it is called as NaCl. It is also referred to as common salt. It is also referred to as common salt, and the percentage or the proportion of NaCl in the oceans is approximately 78%. So this is the proportion of, or this is the proportion of salts in the ocean floor. So in the oceanic waters, so of all the salts in the oceans, so the concentration of NaCl is 78%. Okay, the salinity of the oceans is expressed as amounts of salt per part million or per million parts, and it is expressed like this. Okay, so this is the expression of the salinity of the oceans. It is measured as expressed of salts in 1000 parts. So the salinity of the oceans is expressed as how it is measured or expressed as parts of salt, as parts of salts, as parts of salts per thousand parts of seawater, per thousand parts of seawater, per thousand parts of seawater. So this is how the salinity of the oceans is expressed. So please get this straight. How is the salinity of the oceans expressed? It is expressed like this, as the parts of salt per thousand parts of seawater, and the representative salinity of the ocean is taken to be the salinity of Atlantic Ocean, and the salinity of Atlantic Ocean is between 30 to 35 parts per thousand. So this is the representative salinity of the oceans, which is taken as the reference point. The most common salt of the ocean, you have four salts in the ocean. Out of that, 78% is NaCl. In general, how is the salinity of the oceans expressed? It is expressed as parts of salts per thousand parts of seawater. So if I'm considering 1000 parts of seawater, in that how many parts I'm having salt? So 30 to 35 parts per thousand, this is the average salinity of the Atlantic Ocean, and this is taken to be the representative salinity of the oceans. And the most saline or the most saline water bodies in the world are where? So the most saline water body of the world, let me open up the map so that you get the difference. Okay, the most saline water body of the world is in Turkey. Okay, this part of Turkey, you can, if you can see this pale blue dot over here, let me just see whether you can see this dot. So the most saline water body of the world is in Turkey. This pale blue dot, this is called as Lake Van. Okay, let me just write it somewhere else so that you get a bird's eye view. So the most saline water body of the world is Lake Van of Turkey. This is Lake Van. the most saline water body of the world, and the salinity of this is approximately 4 parts of salt per 1000 parts of water. And next, the most saline water body of the world is over here. This is called as Lake Urmia. This is called as Lake Urmia of Iran, and the salinity of Urmia water body is 300 parts per thousand. And you also have a sea over here. This is called as Dead Sea. Okay, the salinity of Dead Sea ranges between 300 to 350 parts per thousand. So if somebody is asking you which is the most saline water body in the world, the most saline water body in the world is not Dead Sea. The most saline water body in the world is Lake Van of Turkey. This small blue dot. And what is the salinity of it? The salinity is approximately 400 parts per thousand. And then you have Lake Urmia of Iran. It is approximately 350 parts per thousand. And then you also have Dead Sea. It ranges between 300 to 350. So please keep this in mind. Okay. Some estimate the salinity of Lake Van to be around 450. Okay. The salinity of Lake Van is as high as 450. In the summers, when you have even more evaporation, the salinity will increase. So in summers, the salinity of Lake Van can touch 450. In summers, the salinity of Urmia can touch 350, and Dead Sea it can even touch 350. So these three are the most saline water bodies of the entire world. And again, if we consider the variations of salinity, the same thing will happen with regards to salinity too. Why so? Because at the equator, again, because of fresh water addition by the rainfall, the salinity of the waters at the equator will not be as high as compared to salinity of the waters at the tropical areas. So again, if I'm painting the picture for you all, like how is the variation of salinity with regard to the depth of the ocean floor? So again, the same diagram. So this is the depth, sorry, this is the salinity. This is the salinity over here. Okay, this is the salinity and this is the depth. Okay, in this scale, okay, this is the average salinity of the Atlantic Ocean, 30 to 35 parts per thousand, average salinity of the ocean. Between 500 meters and 1000 meters, you will have a layer called as halocline. Okay, similar to that of the thermocline. So halocline will act as a lead. It will act as a lead between the more saline waters at the surface and the less saline waters below. And halocline will coincide with thermocline. So thermocline and halocline will coincide the same. So again, the highest salinity you will find in the tropical areas. From the tropical areas, the salinity will become like this. At the equatorial areas, again, the salinity will be slightly less because of heavy rainfall. At the temperate areas, the salinity will be somewhat like this. And at the poles, again, you will have the reverse trend. Why? Because of the amorphous expansion of the water. Because if cooled below 4 degrees Celsius, it expands instead of contracting. So this is with regards to the salinity of the ocean. The same trend that we observed in the temperature, the same thing we observed into the salinity part. Okay. So this is with regards to temperature and salinity of the oceans. Now, the oceanic waters on Earth are not stagnant. Okay. They are basically moving. They basically move in what sense? They basically move in gyres. And these gyres basically manifest as ocean currents. So in every hemisphere, you will have oceanic gyres, and that oceanic gyres will translate into oceanic currents. Okay, so I will not be venturing into discussion of ocean currents. You just need to remember that the ocean currents are happening because of what? The ocean currents are basically currents happening due to winds. So on the surface you have winds moving. These winds will carry the waters with them. So winds will impart their momentum to the waters, and as the wind moves, the waters will be pulled along with the wind. So you have two types of ocean currents. You have warm ocean currents and you have cold ocean currents. So warm ocean currents will carry the warm waters from the tropical areas, from the equatorial areas towards the poles, and the cold ocean currents will carry the cold waters from the poles towards the tropical areas. So in every hemisphere, you will have an oceanic gyre. How is that gyre and how it basically translates into that we will understand when we will do the North America's atlas. So here I take your leave for today, and from tomorrow onwards, we will begin with the detailed discussion of the atlas. So finally, this moment has come. It gives me immense joy that now I have completed one subsection of our curriculum. From tomorrow onwards, we can basically start our detailed understanding of the Earth's atlas. So from tomorrow onwards, guys, we will be venturing into the atlas sessions, and we will beginning with New Zealand tomorrow. So everyone, please be ready with Orient Black Swan School Atlas, the 8th edition. And from tomorrow onwards, our gears will change. Now, I won't be focusing on the geophysical aspects, but more on the locational aspects. So from tomorrow onwards, keep a pen and paper ready with you so that you are jotting down the points. Vishal, yes, you do have the effect of Coriolis force on ocean currents. The turning of ocean currents is basically because of Coriolis force only. Okay. So the oceanic gyres in the northern hemisphere are clockwise and they are anti-clockwise in the southern hemisphere. It is because of Coriolis force only. But these discussions we will do when we will do the Africa and the North America. So we will go into details of that. But for now, just understand that yes, you have ocean currents, warm ocean current and cold ocean current. Okay. So guys, tomorrow onwards, please be ready. We will be venturing into the New Zealand. After New Zealand, Australia. After Australia, we'll do North America, South America, Africa, Europe, Asia, Southeast Asia, and lastly Oceania. So we will take sweet time amount of around 15 to 20 lectures for doing all of this, and it's my best zeal and it's my endeavor that you all come in consonance with me. Okay. So I am reiterating my name for you all, guys. My name is Pritesh Maturkar. I will be your primary faculty for handling the GS part of geography discourse. So you can all reach out to me on a Telegram channel called as Geography by Pritesh Maturkar. For doing so, you can just do a global search on Telegram at Geography by Pritesh. Using this, you can join this channel wherein I keep on posting the relevant current affairs with regards to geography. So those of you are watching me now, please understand that from tomorrow we'll be shifting our gears. I won't be venturing into discussions of the data sets. We'll be directly opening up the maps and we'll doing the maps in detail. So on the behalf of StudyIQ IAS English, everyone guys, I take your leave. I hope you are doing fine and that you are working hard and smart, and please be consistent because that is the demand of the civil services examination. So take care everyone. Bye bye. Idea scenario.